Welcome to the another session in Frontiers in CFD. So today's simulation will be CFD simulation of heat dissipation from an aluminum heatsink. These are the objectives: to create a 3D geometry of aluminum heatsink using ANSYS design modeler, to generate suitable computational mesh and apply name selection to the fluid and solid domains, to set up and analyze the heat dissipation from aluminum heatsink using ANSYS Fluent. So let's start with the fluid flow Fluent option. On the left hand side, you'll see the fluid flow Fluent option. Open the new design modeler geometry. So first of all, set the units to millimeter. Click on XY plane. We need to generate a primitive, let us say box. The dimensions of the box we have to follow. First of all, make it add to frozen. X component will take it 43, Y component will take it 50, and Z component will take it 31. So first of all, we'll generate this box. Click on generate. Then click on new plane. Base plane we have to take YZ. Then we'll offset this Z by equal to 1. So make it generate. Once it is generated, we have to slice with respect to this plane. Make it generate one more time. Now you can see the plane is used for slicing the object. Now the separation between them will be equal to 5 mm. So accordingly, one more time we create new plane at a distance of 5 mm. One more time generate. Click on slice operation. Click on generate. One more time offset Z, that is equal to 1. Click on generate. Do the slice operation. Similarly, you have to follow this process till we are living to the end. We have to generate the plane and specify offset Z. Then you have to do the slice operation every time. So this we will continue till the end. So carefully you have to keep the same distance between the two consecutive fins. Offset Z again. Repeat the process till the end. So every time we have taken the offset Z, and from the respective earlier plane we are moving ahead. So we are approaching towards the last. Click on offset Z one more time. 1 mm. Click on slice. Same way, last portion is remaining. Click on offset Z. 1 mm. So you can see now the structure is slightly completed. Now we need to modify this further. Create one more plane. Now reference plane, I will take it XY. So select XY plane, make it apply. Again I will offset it Z by distance that is equal to 15. So enter the distance that is equal to 15. Click on generate, then do the slice operation one more time. Click on generate. One more time, offset Z y equal to 1. Click on generate and then we'll do the slice operation. So once the slice operations are done, I will now form the fluid zone as well as the solid zone which are been available. So one by one we are going to select and check which are the zone will be corresponds to fluid, which will corresponds to solid. So this is selection we are doing. So this is for your fin material, all related fin portion I am going to select. Whichever I want to keep this as a fin material, so that I am going to select here. Carefully you have to do the selection. Now I will do the boolean operation, make it apply and generate. So now you can see the rest of the part I don't want as the solid zone, I want it as fluid zone. So I create boolean operation, make it apply and then generate. So you can see now the regions are separated out. Now we need to add a heat source in this. So for this we might require one more operation which is called as create. I go with the primitive, then with the box. Instead of add material, now we'll make it slice material. The dimensions of the box will enter as x component to be equal to 25, y component 25, z component to be equal to z component to be equal to 1. Then for origin definition, we need to shift the object from the origin. As you can see now, the object is at origin, so we have to shift this at the required place. So you may see the wireframe model which is on the back side. We need to shift this wireframe model at, yeah, you can see now. So we need to shift this wireframe model here. So put x component in the origin definition as 9, y component to be equal to 12, and z component to be equal to 16. Z component to be equal to 16. Now let's make it generate. You can see the wireframe model has appeared. Now this will be your heat source. So let's click on generate. Now you can see the heat source will be available. Now we can proceed for uh, specifying the which one is fluid, which one is solid, which one is fin and other thing. So that we are going to do here. So first of all, we'll change this name to fin because this is a fin material. Then one by one, let's check. This will be air region. Similarly, or the remaining air region will check out once and will form them as a new part, so that it will be easy for us to identify when we are doing the setup. So we are done form new part, give the name as air. Not only specifying air, we have to specify this as a fluid zone. Accordingly, the changes we have to make. This one will be your heat source, so you can specify there as a heat source. This is fin, this is heat source, and this is your air. So for all air, you have to give the same name at the respect to other places. So put it air, second one also air, and so on. So we have to ensure that respective zones corresponds to respective, either it is solid or it is a fluid. So we have to check it once before proceeding. Now let's go with back to the workbench window, save the work, save in a respective folder. Give the suitable name. Saved simulation of aluminum heatsink. You can give the short name as well. Click on save. Now you can proceed for the next steps. Now let's start with the meshing option. So click on mesh, click on edit. The mesh window will appear. If you are getting this error, close the mesh window again. Open it one more time. Click on mesh, click on edit. So fit to window, the object will be visible. First generate the default mesh. We'll check out how many number of nodes and elements are been there. We'll see the statistics. Specify the element size. We'll put it 0.0005 and we'll generate the mesh with this element size. Now let's see once it is generated. We will observe the number of nodes and element. So this is 4,97,332, 9,80,939. So this is the current nodes and element we are having. We'll proceed with this particular nodes and element. So now a few things we have to do is we have to define the inlet outlet. Then we need to define the fin region. So create name selection. So carefully select the all and then make it create name selection. Let's specify this as inlet. Check once if the all 8 parts are there. If it is not there, one more time do the selection and make it apply. You can see now there are 8. Similarly specify the outlet the same way we have done for the inlet. All the region which corresponds to outlet we have to select. Ensure that all of them 8 are selected and accordingly we have to proceed. So one more time just check ensure and 8 are selected. Then next select fin, hide all other bodies. So I select all, then you can click on create name selection. I may specify this as a fin boundary. This will be useful for us in setup part to identify the location of fins. So hide all other bodies, select heat source. Now in addition you may specify air as well, but we'll proceed with the next step. Now we have specified inlet outlet, we have specified fin boundary. You have to click on update. Then once the mesh is updated you can proceed for the next step, that is for your setup. Click on edit. So specify the number of solver processes. Click on double precision. Wait till the object is loaded. Now click on transient, select the gravity minus 9.81. Once it is specified, go to your model, turn the energy equation on. In viscous, I will select K epsilon, enhance wall treatment, thermal effect, and curvature correction. Make it OK. Then we are not turning on the solid friction melting, but if it is a PCM metal, then in that case we can add it. So we have the fluid metal by default air, solid metal by default aluminum. We are not going to make any change here. We'll keep this as it is, but if you want some different material for your fin, you can accordingly add the material in the respective case. So air by default the fluid material is there, then fin and heat source. So this we'll see only one option, and that's why we don't need to much worry about this. Then fin, again there is only one option available. If you want heat source maybe of different metal, you need to add the material from the library. So here in the source term I am providing the heat source. Here let's put some heat generation per unit volume. Click on OK. Click on apply, then click on close. Then go to the boundary conditions. Put some velocity at inlet. You can put various velocities. Let's start with 0.25 meter per second. Click on apply, then click on close. So we don't need to make any change here. We will keep it this as it is, as we don't have any other additional material involved. So next step is to go towards the report definition, but we'll define the report definition at a later stage. First of all, we'll set the animation so that we will be able to visualize which part subjected as place where, so that it will not be any kind of confusion when we go back to report definition. So that's why first we'll set the animation so that it will be easy for us to locate the object, and accordingly we'll proceed for the next step. So first of all, select temperature, then total temperature of the system. We have to select all, so this will give me system temperature. Now instead of exponential, I will select it float, make it apply, and then close. Click save display, close, and click on contour 1, give the suitable name, let us say system total temperature system animation. Click on OK. Similarly, you have to set one more animation, new object contours. I select total temperature. Now in this case I will select only for specific region, that is fin boundary. So this is what we are done in mesh, that's why we are able to locate this object quite easily. Otherwise it could have been very difficult to identify the object, and that's why this is important step we are done in the mesh is helpful for us here. Then click on save display, click on close, then click on contour 2, give the suitable name, let us say fin temperature animation. Click on OK. Now we are able to locate where the object is, so easily we can go to the report definition and set things. So this is always better practice to first set the animation so that we can realize where the object is, and accordingly things can be done more properly. So system temperature report definition, click on OK. Next, surface report, area weighted average, temperature. Now here also we consider total temperature. Now we'll select only fin region. We want temperature for the fin, so we'll selecting only fin region, and accordingly print to console, and let us specify fin temperature report definition. Make it OK. Then close, click on run calculations. So number of time step we need to specify. So let's say initially we are taking it 10. Click on calculate, and let's start running the simulation. So we are running it for some 10 time steps at the initial stage. Again, this may not be sufficient, we may have to run this further. So we'll check out first what will happen after 10 time steps, and then we'll continue to run this further. You can see the scale residual. So after the first 20 iterations have been completed, all the windows which we have set, they will be visible. Animation windows, then report curves which we have specified, so they will be visible one by one. As you can see here, the source term which we have specified, that is also been visible. You can see the heated region over there. So this is the total temperature system temperature. This is the fin temperature report definition. This curves will get. Then contours of total temperature, animation window. This is also the total temperature of system. So likewise, the things are there. This is scale residual. We definitely have to wait for some time in order to check how the curve will behave, how the temperature of the system will change with respect to time. So 7 time steps are remaining. You can see certain variations which are taking place. Again, as I said, we have to run it for some long time. So now you can see after performing 10 time steps, this is the things which are available with us. So 300.32. So this is what variation we can observe. As I said, this is again, we have to run it further to visualize it in more better way. So first of all, save the work and then we'll run the simulation again. So directly we'll put it for 90 so that we can see a considerable change. So the calculation is completed. You can see it now. System temperature curve. So this has become quite red. So 301.60. So this is the variation we are able to see. Click on save button. In this way we can visualize the system temperatures. We can run it further, so I can click on few more 100 and let's click on calculate. We'll wait for some time to visualize this completely again after 100 time steps. So we have taken the velocity, that is 0.25 meter per second. The simulation is completed for around 600 seconds. We can now visualize scale residual. The temperature curve has become flat. This is for your system temperature. Then this is the fin temperature which we are having. Then this is the contours of total temperature of fin. This is the contours of total temperature of system. So this is what we have generated for 600 seconds. Now we'll quickly save the simulation. We can save the image file as well. So for doing the saving the animation video, just click on playback, set the animation frames to video frame, then select the number of frames per second here. So here I will put instead of original resolution, I will first select the 4K. In advanced quality, I will just go with the best option and click on OK. Then click on close. At the end, you have to click on simulation report. So you can click on this report outline and you have to click on generate report. So once this is done, your report will be generated, the process will get complete, and after that you will be able to visualize the video as well as the animation images as well. So this process may take some time. We'll wait for the process to get it 100%, and then we'll check out the result. The report is generated. Now you can see the ANSYS simulation report. If you want to visualize the files, you have to go inside of whatever folder you are having. So this is my folder. Inside of that DP0FFF Fluent, you will see the video file as well as the report definition file also. So first we are seeing the total temperature system report file. Now we'll see the fin temperature report file as well. So this is system temperature report file. You have to open it with the help of notepad. Similarly, you will see fin temperature file as well. Fin temperature report definition. So we have to right click and this notepad file will open. You have to copy all these values on your Excel file. So we have copied that value. So you can see now we can plot graph also. So this is for your system temperature. So let's define this as system temperature. Second thing which we are having, so we'll define this as fin temperature. So both are at values, that is velocity, that is 0.25 meter per second. Now what I will do, I will close the Excel file. Now we'll go back to your this file also I will close. Go back to your now we'll run the simulation with different flow velocity. So let's save as this work. I will click as a new folder here, and in that new folder I will prepare this now. So aluminum heat sink flow velocity I will take it now 1 meter per second. Earlier we have taken 0.425. So we are now saving this file with 1 meter per second, and accordingly we will now run the simulation for 1 meter per second. So we need to just do some slight modification in that. So once you will see aluminum heat sink 1 meter per second here. Now you go to the boundary conditions, go to the inlet here, change your velocity to the respective value which we are taking now. So let's say 1 meter per second, click on apply here. Then you have to go to initialization. I just go to initialize, click on initialize. Once this is done, you can see here. Now go back to your respective folder. So let's go back to the folder here. So this is a new folder where we are doing it for 0.25 1 meter per second. So this backup file I will delete. Then one more time I just go here and click on initialize here. Once it is initialized with the new boundary condition, that is 1 meter per second as a velocity, we'll run the simulation again. So this is how the simple step that we can follow, and everything will remains as it is. We don't need to change anything else. Now we will run the simulation for that particular 1 meter per second. So what you have to do, I just need to click on calculate. And we have to run the simulation for some again 600 seconds, and then we'll compare the two values with velocity that is 0.25 and with velocity that is 1 meter per second. What is the change which is occurring in the system? Once this 20 iterations are completed, you will be able to see again the same graphics which will be visible, like total temperature, system, fin temperature, and other graph. So this graph will be again visible, and accordingly again we can generate the simulation as well. So once this 20 are completed, you will see this scale residual, system temperature, and animation windows will be visible. Okay, you can see now the things are again starting here from 0. So we have to wait for some time and we'll check the comparison of 1 meter per second and 0.25 meter per second. This represents the system temperature with respect to flow time. We have two velocities, 0.25 meter per second and 1 meter per second. So clearly the system temperature at 0.25 meter per second is comparatively higher as compared to 1 meter per second. This represents the fin temperature with respect to flow time. We have two velocities, 1.25 meter per second and 1 meter per second. So clearly here also we can visualize the fin with velocity 0.25 meters per second is having higher temperature.